context of chapter 16 and of the kind of mathematics that we'll be working with the rest of our semester, we have the word field, and as I've said there, it's a special kind of function, and it involves vectors. Those are 2 points to make that are implied when you hear the word field. And so there are 3 situations that you could have where something involves a vector valued function. You could have a scalar domain and then a vector valued. Remember that a function, first of all, is a set of pairs of objects. And they're paired by a rule so that for whatever you put first, there is exactly one answer to what you put second. And this is true in algebra and so on. And it's the same idea here. So what I'm getting at is you could have a scalar valued function, and you could be, your rule of pairing could be to take a scalar value, a number say, and put a vector with it as the second object in the set of pairs that you call your vector valued function then. So what's first is not vector and what's second is. Okay, the del operator from chapter 14, which we've studied, the gradient does that, because if you think about the gradient, you think about your surface, like say on the third test, you've got the hemisphere surface. Okay, so you do the gradient, and at any point you're taking the scalar coordinates of the point and you're pairing that with a vector value, which is an arrow that points, if you remember, normal to the surface, okay, at that point. And so scalar domain vector value field then. The del operator applied to a scalar function. Anything you did in chapter 14 with getting the gradient is that kind of thing. Now, you could also have a vector domain and then a scalar value. So this you could make by taking the same del operator. You remember what it does is it takes the partial derivative with x, and that's the that whatever you get would be the I component, or the first component, partial with xi, and then partial with yj, and then partial with zk. So if you do the dot product of del with a vector, you get what we call the divergence of that vector or that field. You can use the word field or vector interchangeably here. And so we write it div for divergence, parentheses f. The f, you see, would be boldface type in the book, has the arrow on it. So that's a vector field. So for example, if you're thinking 3 component vectors, if your field is a vector like this, where the m, n, and p are differentiable functions of x, y, and z, then you can do del dot f. So it'll be the partial of this one with x, plus the partial of this one with y, plus the partial of that one with z. And you see this is a scalar value. It isn't necessarily a constant, but there isn't any little I or j or k in this. So it turns out that the result here, called the divergence, has importance in physics and fluid mechanics and in electrical engineering and so on. And then finally, the third situation that we work with has vector domain and vector valued field for the range. And we can produce that by taking the del operator and the cross product form with a field. Del cross F, one of the people in 19th century physics who worked with these ideas was a Scottish physicist named Maxwell. And if you notice on my syllabus, what we will do the last week of class is talk about what are called the Maxwell equations, which two of which involve divergence, and the other two involve what Maxwell called the curl, which is this del cross F, and they are the four fundamental differential equations for working with electromagnetic fields. So that week is primarily a poor person's physics course rather than, but it's physics where we're applying the ideas of chapter 6. So just a minute. This field that you get, if you do the cross product del cross a vector function or vector field, the curl, a person named George Gabriel Stokes, who taught at Cambridge from approximately from 1850 to when he died, which was 1902 or something similar to that, called it the rotation, which is really what it's measuring. And so the abbreviation then would be ROTF. And you have a little Scottish nationalism here, you see, between whether you call it curl or call it rotation. Books printed in this country all use curl, so Maxwell seems to have won out. Anyway, you're setting this up as you would a cross product. So you have your I, J, K, your partials, and your M, N, and P. And so you see, if you honor the professional football team and work this out, for your first component, or I, you're going to have partial of P with respect to Y, and then coming the other way for the I component here, you're going to have partial of N with respect to Z. And then J, you're going to have partial of M with Z, and back the other way, partial of P with X. And then finally, the K component of curl, you're going to have partial of N with X minus the partial of M with Y. And I believe it's a bad mistake to try and memorize this. I think the thing to do is just go through your 3x3 determinant for the cross product and grind the thing out as you need it, or else find where it is in the book. The book gives this as curl F, and then if you have it written out in front of you as a formula in a problem, then you can follow the formula. But if you try to just memorize this thing, you're very likely to get something mixed up. I would, being honest with you. So I think I do this, or else find the page where you see this. This is in your book. I'm not sure whether it's in section 16.1, but we'll work with it the whole chapter 16. And the book doesn't start out telling you about the three different situations that we associate with a vector field, but I believe that it should. So what I'm doing here is not word for word what's in 16.1. So before we go on here, let's take a look at a couple of the handouts that you just received. First of all, the one with the colored picture that says page 927. This is actually copied from your book. Maybe it's the 12th edition, so the page may be wrong, but it's in your book. And you see what they're trying to do there is to show you examples of fields, which you see are vector functions, so you see the vectors. So one way that you can understand a field, I think, is with this weather map, if you want to say that. You can recognize South America and Africa and Europe in the picture. And you see, then you can represent your vector field. The arrows that are in there in white show the direction of the wind, and the colored background would be the way that you could see the magnitude. So you see where it's yellow is the maximum in the picture of the field, meters per second. And so 14, 15 meters per second is pretty hard wind. And so you see there are various storms and throughout where the yellow is, and so on like that. So that's a way to display a field. And then they're talking about gradient fields. If you turn the page over, they're talking about vector fields. If you'll notice, it says vector fields, and then there's a fairly lengthy paragraph, and then there's a sentence: generally a vector field is a function that assigns a vector to each point in its domain. So I was talking about that. And then they're talking there about the gradient, which we studied in chapter 14, and then these other fields are what we're going on with. Look where your set of notes that has my handwriting. And you see I'm talking on the first page here about divergence and curl, which is what's on the board. So to understand curl, first of all, think of what we would call a flow. So imagine that there's a big water main that's in that wall over there, and that it has broken, and so we've got a flood going across the floor. And so you could think of that as a flow, and suppose you had something that's very light, like a ping pong ball that's floating along in it, or something that would be, well, for example, if you have a dispenser for Scotch tape, the kind where you can buy the rolls and refill it, okay? The little wheel thing that the new roll goes around, if you think of it, if you took it out of the dispenser, you've got what would look like a little paddle wheel. It has an axle on each end and then the round part. So you could think of a little paddle wheel in this flow. So that means that if you have a change in the velocity from one side of the wheel to the other, it's going to make it rotate, right? And so that means if you're looking at the top of my page here, these fields that I have, if you have the arrow as if you have the length of the arrow as the velocity of the water that's flowing, if you look at something like A, where the arrows all have the same length and they're all pointed the same way, then the one side of your paddle wheel isn't going any faster than the other, so it wouldn't be trying to rotate. But if you have something where you look at something like B, well, let's see. Well, certainly if you look at D, you can certainly see that there is a rotation, but you can also get a rotation in something like B, where either there is a whipsaw sort of thing where the arrows are going in one direction on one side and in the other direction on the other side, or just simply if they're longer on one side than the other, so one side's going faster. Any of those things will make it rotate. So a curl has to do with rotation, but it doesn't require that the arrows are going in so obviously a rotational pattern as picture 4 across the top of the page. So
in picture D.
B, yeah. So then let's look at what I'm calling a rotation. In the handwritten notes, if you turn the page, what I am doing here is on the back of the first page. So what we call a rotation then, you have a point, and this would be like the center of your ping pong ball or your paddle wheel, and it has a translational velocity V. That's the velocity of the water that's flooding the floor, going out the door, say. And then you have a point at, say, x0, y0, z0. And you have a radius and another point x, y, z out here, also going with translational velocity v. So whether or not this is rotating is whether or not a rotational vector omega is or isn't 0. So what we have is that the translational velocity out here in the tangent is the rotational vector omega crossed with the radius r. So this r is a vector. So if we think of the rotational vector as having components 1, 2, and 3, and we think of the r as the vector from fixed point to variable point, so that's the r vector. If we do the cross product, then going through the same thing with the 3 by 3 determinant, you see what we get. With the I, we have omega 2 z minus z0, and then coming back for the other way for the I, we have omega 3 y minus y0, and then with J we have omega 3 x minus x0, and back the other way, omega 1 z minus z0, and then finally K omega 1 y minus y0, and back omega 2 x minus x0. So this would give us our translational velocity related to whatever is our rotational velocity vector, where you're measuring the translational velocity at some point x, y, z, and measuring the rotational velocity at some point x0, y0, z0. So this is our cross product. I haven't shown you yet what the curl has to do with this, but we're getting there. So now, if this is V, defined as this cross product, do curl V, and I will show you that what you get is twice the rotational vector omega. So the curl of the translational velocity is twice the rotational velocity vector. So that means then that if curl is 0, then the rotational vector is 0. So you say curl 0 means irrotational. And as you could see in those pictures, you could get a non-zero curl not just by a field where you see the vectors going around in a circle like the right-hand picture there, but also if you have pictures where the arrows are aligned parallel but of varying length, so that one side would have more translational velocity than the other. That'll make it spin. So you see that you get the curl as twice this if you go ahead now with the V that is here and do the curl, which as a cross product, you see, would be the del cross this vector. So what I'm doing here with my blue and orange arrows is del cross this. So how do you do the cross product again? Well, you have I, J, K, partial with X, partial with Y, partial with Z, and then my components for my translational velocity, which is defined as rotational velocity cross R, where the R is from where the rotational vector is to where you are measuring the translational velocity. And the omega cross R vector is this line. So here's what would be its X component, its Y component, its Z component, X and Y repeated. And so doing this same kind of thing, you have the I, the partial with Y, and this. Well, you see, partial right here with Y gives you omega 1. That's a constant, and the partial of X with Y is 0, and that's a constant. So that gets you the omega 1 I. And then in the same way, J partial with Z, this one gets you the omega 2 J, partial of Z with Z is 1, partial of Y with Z is 0, and those are constants. And then partial with X of this gives you omega 3K. So those are the three in blue for the slants like this. So that's the same as doing these, or here, the same as doing these, you see. And then coming back, you have your 3 in orange, which is this line, and then you take the blue minus the orange, and you see you have 2 omega 1, 2 omega 2, and 2 omega 3. So what I've done here is to prove to you that curl V really is 2 times this vector, which is what we're calling omega. So if there's rotation, there's non-zero curl. And if there's zero curl, there's zero rotation. And this is important not just in electricity and magnetism, as we'll see in the last week of class when we talk about what are called the Maxwell equations, but it's also important in hydrodynamics. I think you can see that it would be. So then, what about divergence? That represents the time rate of mass flow per unit volume of fluid away from, if the divergence is positive, or toward, if the divergence is negative, a point at some coordinates. So you could think of your point here in a box, and think of the box as if it has sides that are not impeding a flow of whatever is your fluid. So a screen, and where you're not worrying about issues of frictional drag because the fluid is trying to get through the screen. The screen that's there in imagination, but not really in the way, so to speak. Okay, and so notice that your fluid might or might not be compressible. If you're thinking of something like air, it's quite compressible. You're thinking of something like water, well, not so much. It is, but you have to press it pretty hard. Okay. So if you had a variable density, that could depend on the geometric position. It could depend on X, Y, Z, and also depend on time, certainly. And so divergence then can vary either with change in density, with change due to source, like inside your screen sided box. Maybe if you're thinking of water, you have a faucet that's turned on. So we have this flow coming in, say if you're thinking of water, so then I'm not worrying about the change in density. And then I find a place in my domain where there's a faucet turned on, so there's more water, and then I'm looking at what comes out. So presumably at least some of this is coming out with what was going in, so the arrows coming out are longer than the arrows going in. So that's positive divergence. The idea is divergence away, but divergence like this in the sense of the arm waving, right? If I knew anything about music, you can see where I would naturally go. Okay, then on the other hand, you might have a sink, you might have a drain there. So you've got water coming in and some of it goes down the drain, but maybe it's coming in so fast that it can't all go down the drain, and so there's still some more coming on through, but these are shorter arrows. So that's the sink, which is what a sink does after all. You could think of your kitchen sink, and it depends on what water flow you have. It may be if you turn your faucet clear on, it'll flood over. it'll come in faster than it can go down your drain, right? So you could have that or not. It could be that either as I've said it or as I've drawn it there. So we can have source essentially with a positive divergence or sink with a negative divergence. And divergence 0 then would mean that you just have a pass-through, flow in, flow out, same amount of material. Notice that if you're thinking of water, then this analogy with faucet and drain works pretty well, but if you're thinking of a gas, it's more complicated because you can be compressing the fluid or you can be expanding it. So there's then not just it's not as simple perhaps as a velocity type of situation like this where you are putting more in or taking part or all of it out because of the issue of the compressing or expanding. You get into this if you're really doing hydrodynamics, but we don't have to worry about it for our purposes, which is to understand the basic idea of what divergence is. So it's probably easier to just think in terms of something like water. Okay, so then it's time to get at, well, how do you do the homework? Okay, so that's over here. What we will be calling line integrals. Take a look at the maple. And so what they want you to do, first of all, is get the idea of a parameterized curve. And this is what we were doing in chapters 12 and 13. Chapter 12, the curve was always a line, and chapter 13, we remember the second test, you had the position vector tracing out the curve, and the t then was your parameter. So in the problems 1 through 8, what they're after you to do is to get an understanding of how the curve might look. So if you were using maple, for instance, you could type space curve, and then they're giving you the parameterization as a vector. So the very first one, say t and 1 minus t and 0. So what you have is a line that's in the xy plane. So the green then would be the curve. I've done that twice, once with normal axes and once with boxed axes. And then with problem 5, you're still talking about a line. X is t, y is t, z is t. And if you turn the page, you see the slanted line. And then problem 7 is actually a parabola, and you see how that looks. A couple of shots of it. And then 8, you have the curve that you see that is in the XZ plane, and it looks like an arch. Then if you turn to the back of your second sheet of paper, we start to talk about these integrals along a curve, which I have here, and we'll go through these in just a minute. It's possible to get Maple to do those. And then if you look at the third sheet of paper, let's see. I think that the third sheet of paper is backwards, that you the rest of this really goes with the section 16.2, and these are fields where you see the field plot. So that goes with what we'll do tomorrow. So let's look at doing parameterized integrals. So if you write a curve in parametric form, we can use the parameterization of our curve to rewrite an integral that's supposed to be carried out along this curve in terms of the parameter. So in this way, we have expressed the integral correctly along the curve in terms of t. So for instance, look at problem 10 in 16.1. So what they want us to do is the integral of this scalar function along a curve, which they tell us is a line segment. So we want the integral of this function of x, y, z ds, where s would be the arc length along this line segment. So the first thing you have to do is to, if you're doing this by hand, is to parameterize your curve. So you want to write the line from here to there in parametric form. So you need the direction vector. We're back in chapter 12. This is what we were doing in chapter 12. Vector from and to, it's this minus that, this minus that, this minus that. That would be your, what I called capital L in chapter 12, the direction vector for your line. So 1 minus 0, comma, 0 minus 1, 1 minus 1. So then your line is from the point, the problem says C is the line segment from to. So you take the point where it's from, x minus 0, y minus 1, z minus 1 is your parameter times your direction vector. And so that gives you, like you did on the first test in chapter 12, to get the parametric equations of this line segment, t, 1 minus t, and z is 1. And when you're doing these line segments from somewhere to somewhere, like this, at t equals 0, you're at the starting point. T equal 1, you're at the ending point. So your limits on t will be 0 to 1 if it's this kind of parameterization. So the r of t that traces this line then is r equals x, y, z, x, y, z. So then you can do dr dt, which is your vector velocity, derivative derivative. Then ds dt square, s is arc length, is velocity dotted with velocity. This is just like chapter 13 in your second test. So in this case, that's 2. So ds dt is square root of 2. So what you want to do then is replace x in terms of t with what x is if you're on this line. Replace y in terms of t with what y is if you're on this line. Z in terms of t by what is z, even if it's a constant. And then ds is ds dt, your square root of the dot product of velocity with itself times dt. So that's what I've done down here. I've replaced x with t, y with 1 minus t, and that minus sign is this one. Z with 1, constant with itself, and then the ds dt dt. This is ds dt, and that's dt. Okay, so now you have an integration to do like Math 170. You see, it's all just involves t and numbers. And if you collect your terms, you have 2t minus 1 plus 1, and then minus 2. And then you integrate that from 0 to 1, because that's the limits on your parameterization. And you can factor this root 2 out in front, and you get what the book has, minus square root 2. So if you look in your maple, I think I may have done problem 10. So I'm on the back side of the fourth sheet of paper. You see my typing in capital letters, parameterized integrals. We use the parameterization to compute the integral. That's what I've just done. People call these line integrals. So, however, the path may be some contour other than line, so it's better to call them contour integrals if you're being picky.
I'm not finding it.
Beg pardon?
I'm not finding it.
On the second sheet of paper, on the back side,
Oh, on the second sheet, okay.
right?
Okay.
Okay. And so Maple has various ways to work parameterized integrals. So they're parameterized with respect to the arc length, you see. And if you use the student package, it has the command line int. And if you use the vector calculus package, it has the command path int. And so it has two ways you could do this. So looking at problem problem 10, 16.1, number 10, I bring up the student package, you see, with student, and then I type line int, capital L on it. I type my original integram. The problem in the book looks like this. So I type this, x minus y plus z minus 2. And then I am typing in the parameterization, which I have to get. You see if I'm doing it this way, which is here. And the limits on t, and back comes 0 to 1, the 2t minus 2 is this, and then all that in the square root is the dsdt computation. See, what it is the computation of doing this derivative and then dotting it with itself and then square rooting that. So that's why the square root sign and the sum of the squares. And if you want Maple to simplify it, then you see line 2, what's number 2, and then if you want the value, you see the answer, which is number 3, which is what I have here. If you do it with vector calculus and type pathint, notice a capital on the P and a capital on the I of int. You put in your curve, and then you can say that your path, so you have to give your coordinates. With vector calculus, you always have to say what coordinates you're using. So Cartesian, x, y, z. Equals line, you're telling it it's a line and from and to. 0, 1, 1, 2, 1, 0, 1. So you don't have, if you're using vector calculus and pathint, you don't actually have to figure out this parameterization that we do with student or doing it by hand. It does that for you, and it'll just tell you the answer. Of course, it doesn't tell you how it did it, but you can't have everything from computers. You can either get them to tell you the answer if they don't screw up, or you've got to figure it out yourself how they did it. Okay. But anyway, these can be done with Maple. So notice, as I said this already, but I have it in writing here, if you're doing the parameterization of a line segment between 2 points, then your parameter is going to run 0 to 1. At t equals 0, you're at your starting point from, and at t equals 1, you're at your end point, like that. Many of these problems are not line segments, and then they tell you what the parameterization is, and they tell you what limits to take with the t. Look at problem 12. The curve is a helix, coil, spring sort of thing. So you're going around in a circle, you see, with radius 4, and you're climbing from the z. And they're telling you the limits on t. So this is more typical, where they've given you the parameterization and the limits. So then you can do your dr dt, as you did in chapter 13, say, and this is basic derivatives. Then you can do dr dt dotted with itself, and that's your square speed. So 16 is a common factor. You have sine square plus cosine square plus 9. So you really have 16 and 9, and then the square root is the 5. So the original problem then is to do the integral of this expression on this curve. So integral on the curve, that's the curve is this helix traced by this. And so you have your limits on t. You see you can replace x now from back to your parameterization. This is x, this is y, this is z. So x squared is 16 cosine square, y squared is 16 sine square. They don't use Z in the problem. And the ds is ds dt, which is 5 dt. So this is the ds part. Okay, so you're going to take this 5 and the 4 from the square root of 16 and integrate that, minus 2 pi to 2 pi, and you get 80 pi. Now let's look at our maple. So if you do line int, then you have to put in what the parameterization is and the limits. And you see line 5 there, you see the square root and the you see this, the square root of 16, cosine square plus sine square, and the 5 comes from the second square root sign, where you have the derivative of 4 cosine quantity square plus derivative of 4 sine quantity square plus derivative of 3t quantity square, and so on. So simplify is line 6, you got 20, and then the integral, you have this. If you say 20 instead of 4 times 5, and then the value is 85. Then if you wanted to do it with path int, you do set coordinates and the path like that, and then what I was saying, I got this next sheet of paper backwards. I got something out. Maybe what I have is something missing there. Okay. I don't, looks like we lost a sheet of paper or something. Well, so I guess that's as much maple as we get there. Meanwhile, let's take a look at 33, which wants the mass of a wire for which the mass density is given like this. The wire follows a curve traced by the tip of r of t, which is given as this vector. So what we're thinking of is that our application of the line integral is, one application is that if you think of your curve as a wire, then your line integral along that curve from one end to the other will be the mass of the wire if what you have is a function that would give the density. It could also be the total charge if your function were the charge at each point on the wire, things like that. So the problem is thinking your density is 3/2 t, as t varies as you go along the wire with your parameterization. So your wire is bent to the curve that's traced out by the tip of this vector. And so wherever you'd be on the curve, depending on your value of t between 0 and 1, 3/2 times that t would be your density. So it's getting heavier, you see, as you go. So you get your ds dt dt, your arc length, from doing dr dt. See, they've given you the parameterization. So your dr dt is 0, 2t, and 2, dot with itself, and that gets you 4t squared plus 4, which you can rewrite like this, and then your ds dt is the square root, so that's 2 and square root. So your mass is your variable density, your ds, or ds dt, dt if you want. So what's circled in the red here is the ds dt. And so you can factor out the 3/2, and then you can do a u substitution. You see, if this is u, t squared plus 1, you can take the 2 that's here with the t, and that's your, well, the 2t dt is the du. So you have u to the 1/2, then t, and the 2, and the dt is the du. Change your limits to limits on u, and you get this. 35 is the same sort of thing. Curve traced by the tip of this position vector, r vector, as t goes 0 to 1. So you do the dr dt, you get root 2 minus 2t, dot with itself, and you notice that this is 4, 2 plus 2 is 4, so this is 4 plus 4t squared, so 4 times t squared plus 1. And so then there are two parts. The A part wants the mass if delta is 3t, and the B part wants the mass if delta is constant. So the A part, then you put in your delta, 3t, and you have your, from here, you have your ds dt dt. If you factored the 3 out and took the square root of 4 as 2, then you have square root of t squared plus 1 and 2t dt, so you have u to the 1/2 du. If you're saying that u is t squared plus 1, change your limits to limits on u and work that out. If you have constant density, then your mass is really just your arc length. And so your ds dt again from our work down here is the square root of this, so it's 2 square root t squared plus 1. I factored out the 2. Okay, so this depends, what you do here depends on how energetic you are. Okay. You could take a sensible attitude. I passed Math 175. I don't have to prove I can do this integral by hand, and use your graphing calculator or use, look it up in the table in the back of the book and get on with your life. Or you can say, no, I want to review Math 175, in which case you do a trig substitution. If you let t be tangent x, t squared plus 1 is tangent squared plus 1, which is secant squared. And then you have to do dt, which is secant squared dx. and change your limits from limits on t to limits on x, since it's a definite integral. So then you have 2, 0 to pi over 4, square root of secant square, which of course is secant, and secant's positive, so you don't have to worry about the absolute value at least. And then secant squared, which came from your dt. So then you have to do secant cubed. Well, you can integrate that by parts, or you can go back into chapter 8 where they actually work out secant cubed. It's an example in your book there, and you could copy all that. And I ran out of energy to go through all that, but it is there in your book. And anyway, if you either use the formula from the table of integrals or go ahead with the secant cubed, this is what you'll end up with. Okay, meanwhile, let's look at one last problem, number 25. So it wants the integral where your path is a set union of two curves. So your path is the parabola from 0, 0 to 1, 1 in the xy plane. That's curve C1. Together with the return on the line y equal x. But notice the way the arrows point. You're starting at the origin, you're going out on the parabola and back on the line. So I called this C1 and that's C2. So on C1, then you have to parameterize, and you see if you say that x is t, then your y is t squared, because it's this curve. And you have that same kind of thing on the third test, if you remember, where we had those curves down in the xy plane that were parameterized, and then you use that to parameterize the curve up on the surface to do your directional derivative if you wanted to do it as df dt divided by ds dt, which is one of the ways you could do it. So then with R1 and this parameterization, your vector velocity is 1 and 2t and 0, whereas on path 2, you see it's a line, but you have to remember you're going from here back to there. So if you work that out, you'll have 1 minus t, 1 minus t, and 0. And it's because you're going this way, that it's 1 minus t. If you were going this way, it'd be t minus 1. But you have to take into account which way you're going. And again, then your derivatives will be minus 1 and minus 1. And then if you've done that, your parameterization is 0 to 1. Notice when t is 1, right here for the line, your r would be 1 minus 1, 1 minus 1, and 0. You're down there. When t is 0, your r would be 1, 1, 0, which is up here. So this parameterization and these limits on t do have you go this way. So you have to watch for that. Okay, so my ds dt on path 1 is from here. You do the dr1 dt dot with itself, and you get 1 plus 4t squared, and then On this one, you dot this, you do the derivatives, and dot this with itself, and you get 1 plus 1. So then my line integral on the closed path is the sum of the line integrals on the two pieces. That's the reason I'm doing this example, is to explain that if your path is a set union, then your line integral will be the sum of the line integrals on each of the individual paths that make up your set union path. So for the one, I have x is t, and the y, second term is square root of y, so it's the square root of t squared. So there's x plus square root of y on path 1 with the complete, or with the correct dr1 dt dotted with itself and square rooted. And then here it is on path 2, the x is 1 minus t, and then you have square root of 1 minus t, and then the dr2 dt dotted with itself and square rooted and dt. So this one will be a u substitution, and you'll end up with this as your integral, as your value. And this one, you'll end up with these numbers, and then you put these together and you get what the book has. So what we will talk about tomorrow then is is more with the idea of the vector fields, what would lead us to the maple pictures that you see in your handout. I'll try and get these pages in the right order and reprint it for you. And then we'll go on and talk about what are ideas where the line integral is independent of the path, and that leads us to what is called the fundamental theorem of calculus for line integrals, which works if you have the type of field where the value around a line integral is independent of path. That's not always going to be the case, but turns out that we can use the curl idea to tell when it will be so and when it won't be. So it's time, I guess, for you to get the test, right? And I have them here.